All right, let's dive right into this masterclass on exactly what Cambridge examiners are actually looking for when you write pseudocode from Flowcharts. Welcome to the Ultimate Explainer. I like to call this session the boxing match. Computer Science Cambridge Exam Strategy. And think about it like this. To win those top marks in the exam hall, you need to float like a concept and sting like evidence. Seriously, you need a literal jab, cross, hook combination for your answers. Now today we are specifically tackling Cambridge Subject Code 9618. But let me be absolutely clear right out of the gate. These strategies are completely foundational. Whether you're sitting syllabus 0417, 0478, 0983, 0984, 2210, or even if you're studying legacy papers, this is for you. So, flowcharts. They're visual representations, right? You've got your diamonds for decisions, rectangles for processes, parallelograms for inputs and outputs. Translating those abstract geometric shapes into structured logic-driven text, that is pseudocode. It's literally the universal language of Cambridge examiners. Let me set the stage and introduce you to the ultimate challenge we're going to conquer today. I want you to picture two typical students staring down a terrifying, complex past paper question. First, we have Alex. Now, Alex overloads every single answer with raw computer science facts. He just panics and dumps every single piece of syntax he has ever memorized onto the page, but he includes absolutely zero analysis. Then we have Sam. Sam rushes, Sam reads a flowchart, completely panics under the time pressure, completely misses the command word requirements, and just starts writing this unformatted, chaotic code. If we were to take a look at their flawed answers side by side with the examiner's red pen marks, guys, it is a bloodbath. They are both losing massive, massive marks, but for completely different reasons. Today, we are going to fix that, and I'm going to give you the ultimate step-by-step strategy.
Now, what's really interesting about this slide is that it reveals the ultimate secret straight from the Cambridge Principal Examiner report. Examiners reward causal relationships and cross-topic connections over superficial breadth. And listen, this is exactly where our first student, Alex, goes completely wrong. Superficial breadth, meaning just blindly listing every single variable, data type, or loop structure you've ever learned, it absolutely does not impress the examiner. No way. They want to see what they call a connected conceptual understanding. They want to see that when you look at a highly complex flowchart, you actually understand the fundamental why behind the procedural process, not just the what. You see, the exam boards purposefully design scenarios that you have never, ever seen before. If you just rote-learn standard sorting algorithms without understanding how they transfer to completely unfamiliar, weird contexts that the examiners love to invent, you are going to drop a tremendous amount of marks. It is all about analytical depth. You have to prove to the examiner that you can adapt logical principles to absolutely any system they decide to throw at you.
So, here is our roadmap for today's explainer. First, we'll cover the examiner's mindset. Second, the systematic methodology. Third, critical analysis skills. And finally, the top 3 exam mistakes. Let's move right along. Part 1. The examiner's mindset. Unlocking the assessment objectives. Okay, to truly get into the mindset of the person marking your paper, you have to relentlessly decode their command words. Words like describe, evaluate, trace, and write all demand completely different cognitive approaches. When our second student, Sam, rushes through the exam, he treats an evaluate question like a describe question, and by doing that, he literally throws away over half the available marks before his pen even finishes the first sentence. The examiners are constrained by very strict assessment objectives. The Cambridge Assessment Framework absolutely demands logical, structured reasoning rather than just memorizing standard algorithms. They are targeting your knowledge, sure, but more importantly, your application to unfamiliar contexts and your deep analysis. So to conquer these assessment objectives, top-tier students structure their computer science answers using the Peel framework. Think of this as your boxing combination. Jab, point. State your core concept or algorithmic choice clearly. Cross, evidence. Provide a specific, hard example directly from the flowchart or pseudocode provided in the paper. Hook, explanation. Explain exactly why this evidence supports your point and how the code functions mechanically. Uppercut, link. Link it all back to the specific context of the question scenario to secure those application marks. Point, evidence, explanation, link. If you use Peel, you naturally force yourself out of superficial breadth and into the deep analysis that examiners crave. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving on to Part 2. The systematic methodology, and how to earn those crucial method marks.
Look, in a high-stakes exam environment, a tiny syntax error might cost you a single accuracy mark. But if your underlying logical flow is correct, you can still sweep up the vast majority of the method marks. This is literally the difference between a student who gets a C and a student who secures an A-star. The A-star student knows how to milk the mark scheme for every single method mark available, meticulously proving their logic step by step. This step-by-step standardized sequence is your absolute blueprint for tackling any complex flowchart problem. Let's break this down. Step 1. Deconstruct the question. Highlight the command word, identify the context. Step 2. Extract relevant data. What are the variables? What are the initialized values? Step 3. Select your analytical framework. Are you using a for loop, a while loop, or a repeat until loop based on whether the iterations are known or unknown? Step 4. Execute with clear notation. Clear notation means utilizing the exact conventions Cambridge expects. Using the left-pointing arrow for variable assignment, capitalizing keywords like if, then, else, and strictly aligning your indentation. Step 5. Present with correct terminology. Let's look at our two struggling students again. Sam skips step 1 completely, rushes the extraction, and starts writing absolute garbage code. Alex does steps 1 and 2, but completely ignores step 3. He just writes whatever loop he remembers first. If you consistently follow these 5 steps, you build an impenetrable safety net that catches those method marks every single time.
I know interpreting complex binary representations can be incredibly hard, but applying our step-by-step methodology makes it so much more manageable. Imagine a complex 8-bit binary register that a flowchart is asking you to manipulate. When you look at binary, you aren't just looking at ones and zeros. You have to identify the most significant bit, the least significant bit, and truly understand the logic. If a flowchart shows a logical bitwise shift to the left, what happens to the data? Most students panic. But using our methodology, you extract the initial binary value, apply the procedural process, and systematically shift the bits, filling the empty space with a 0. You aren't guessing, you are interpreting. The core trend here is that data extraction must be flawlessly methodical. If you rush the binary extraction, your trace table will be ruined from row 1, and your pseudocode will be fundamentally broken. Take a breath, extract carefully, and then move confidently to the execution phase. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCESE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCESE and turn on all notifications so you never miss our weekly exam strategy sessions.
And this brilliantly illustrates how your data interpretation skills must flow logically from extraction to calculation to evidence-based conclusions to guarantee those method marks. This actually brings us to a really fun concept, finding the flaw. Listen to this flawed sample paragraph that a student like Alex might write during a fast-paced exam. The flowchart uses a loop to check the binary numbers. The loop is a while loop. It stops when the binary number is 11110000. Therefore, the algorithm works. Can you spot the exact sentence losing marks? It's that absolute massive leap at the end. Therefore, the algorithm works. It lacks any evidence-based conclusion. A top-tier response would draw a specific conclusion based on the performance of that loop, stating exactly why that specific binary threshold triggers the exit condition and how it impacts the overarching system. You must pull the data, perform the logic with clear working, and draw an undeniably backed conclusion. That is exactly how you transform red pen marks into green check marks.
Moving to Part 3, Critical Analysis Skills, Evaluating Algorithm Quality.
Now we transition into higher-order assessment objectives, which demand evaluation of alternatives and justified recommendations. This is where the true A-star candidates are separated from the rest of the pack. You see, you aren't just tracing code anymore. You are judging it. You are stepping back, playing the role of the senior software engineer, looking at the flowchart and asking, is this actually the optimal way to achieve the goal? Notice the massive difference here. Top marks require you to rigorously identify how space complexity, time complexity, and edge cases actively affect the algorithm's performance. A superficial evaluation looks like this. This algorithm is good because it uses a for loop, which is easy to read. 0 analytical marks for that. A higher-order evaluation, utilizing our PL framework, sounds like this. Point: the proposed linear search algorithm exhibits poor time complexity for this specific large-scale database. Evidence: the flowchart indicates a sequential search through an array of 50,000 unordered customer records. Explanation: this results in an O of n time complexity, meaning in the worst-case scenario, it must perform 50,000 individual comparisons, which is highly inefficient for real-time processing. Link: therefore, sorting the array and implementing a binary search approach would be significantly more appropriate for this system's rapid response requirements. Do you see the difference? The higher-order answer lands a massive combination of technical terminology and anchors it directly to the problem's context.
When comparing algorithmic approaches, you must use clear comparative connectives and back every single claim with hard evidence.
Words like whereas, conversely, in contrast, and similarly are your best friends here. You cannot just describe algorithm A in one paragraph and algorithm B in the next and leave it up to the examiner to connect the dots. You must actively clash them together. For example, you would write, algorithm A utilizes a dynamic data structure, whereas algorithm B relies on a static array. While algorithm A offers superior space complexity by only allocating memory when needed, algorithm B's static nature provides slightly faster access times, which is of greater relative importance given the strict, low-latency requirements of this specific scenario. See what happened there? You are drawing relative importance conclusions based on evidence? That is how you absolutely dominate the comparative analysis questions and impress the examiner.
Keep these 4 pillars in mind, because efficient code implementation relies entirely on how well you decompose the problem initially. Algorithmic thinking isn't just a buzzword, it is a highly measurable skill. Step-by-step decomposition is the act of breaking a giant, terrifying flowchart down into tiny, manageable subroutines. Once decomposed, you must select the appropriate data structure. If you choose a 1D array when a 2D array is clearly required by the relational data context, your entire code implementation will be fundamentally inefficient, no matter how beautiful your pseudocode indentation is. And finally, rigorous testing. In the exam hall, this means trace tables. Picture a table where every single column represents a variable from your flowchart, and every row represents one full iteration of your loop. As the data updates, you cross out the old value and write the new one. A trace table is your ultimate diagnostic tool to rigorously test the logic of the pseudocode you just derived. Never, ever skip the dry run.
Part 4. Top 3 exam mistakes. These are severe warnings straight from the principal examiner.
Let's look at the harsh reality and uncover the specific pitfalls that destroy candidate scores. Every single examination series, the senior examiners publish a report detailing exactly where students lost marks across the globe. I have painstakingly combed through these reports for the 96-18 syllabus, and the data is crystal clear. Students are making the exact same avoidable errors year after year. If you take away anything today, remember this. Failing to link your points to the specific context of the question is the ultimate classic mistake. This is the classic Alex trap. Alex will write a beautifully formatted textbook definition of a bubble sort, but the question specifically asked how the algorithm tracks student attendance records in a school database. Because Alex never mentioned the words students, attendance, or database, he gets 0 application marks. The examiner's red pen strikes again. The exam paper is not asking for sterile textbook definitions. It is asking you to solve a problem for a specific client or scenario. If your answer could be copy-pasted into a completely different exam question and still technically make sense, it is too generic. You must fiercely anchor your code and your analysis to the scenario provided.
These 3 errors cost students easy marks every single examination series, so be incredibly vigilant about boundary conditions. Let's clearly define the difference, because it absolutely matters. Boundary conditions are the exact, known limits of your acceptable data. If a loop needs to run exactly 10 times, the boundary conditions are iteration 1 and iteration 10. Does your loop stop at 9? Does it accidentally run an 11th time? That's an off by 1 error, and examiners hunt for it aggressively in your pseudocode. Edge cases, on the other hand, are the extreme, sometimes unexpected anomalies of your data inputs. What happens if the user inputs a negative number when the flowchart expects an age? What happens to your array if the binary register overflows and you lose the most significant bit entirely? If your pseudocode does not account for these anomalies, it is brittle. The Cambridge examiner wants robust, bulletproof logic that survives the harshest data conditions.
To ensure you don't panic under the harsh fluorescent lights of the exam hall, I want you to create your own simple memory hack using the first letters of our methodology to lock in the sequence. D-E-S-E-P. Deconstruct, extract, select, execute, present. Think of it as your pre-fight boxing checklist. Before you throw a single punch, before you write a single line of pseudocode, you run through DESEP. It grounds you. It forces you to pause, analyze the flowchart methodically, extract the binary or integer data carefully, and select the optimal loop framework before you ever begin the execution phase. This is exactly how you outsmart the pressure and perform like a top-tier candidate.
So there are 3 cognitive domains to satisfy, 3 major mistakes to avoid, and a structured methodology to earn every method mark. Let's bring this all together into the final computer science success blueprint. Here are the 3 non-negotiable rules that guarantee top marks. Rule 1. Command word decoding. Never start writing until you know exactly what the verb is asking you to do. Rule 2. Peel framework application. Structure your analytical paragraphs with point, evidence, explanation, and link to completely eliminate generic answers. Rule 3. Time management matrix. Allocate your time strictly based on the mark allocation. Do not spend 10 minutes perfectly indenting a 3-mark loop while leaving a 12-mark evaluation question blank. This complete, interconnected answering system is your knockout blow. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
So I leave you with this. Think carefully about your boundary conditions, because a beautiful algorithm that fails on the very first edge case is just a beautiful failure. So as you stare down your next complex flowchart, ask yourself, are you just translating shapes into code, or are you truly building an unbreakable logical system? I'll see you in the next explainer. Keep practicing and stay logical.